Hi, this is Kevin Trainer, and welcome to part two of my lecture on chapter 9 of the third edition of the Zelle Python programming book. And as we finished up part one, we had really finished the design of our game. It's a racquetball simulation game. And we uh, we were able to build a structure chart for the program for levels 1 and 2, and this does a really good job of showing what all the code pieces are in kind of general computer science terms when you divide up your code into these kind of pretty pieces. They're called modules. So this is sometimes called a hierarchy chart or a module chart. In Python, as we're working right now, these pieces are going to be functions. So we have the main functions, and then we have four sub-functions: print intro, get inputs, sim end games, print summary. And the solid lines that connect the boxes or the rectangles, they indicate that the functions on level 2 are all called by main, which is the only function on level 1. And the annotations that run along those solid lines are indicators of the inputs and outputs from the functions. And when we say inputs and outputs, we're talking about the interface between the code in main and the code that we're calling. Now, there might be all kinds of other inputs and outputs that go on within the functions that are called. They might open files, they might read from them, they might write to them, they might get input from the console, they might write input to the console. But uh, that's not what we're trying to describe. What we're trying to describe is what's the relationship between calling code and called code. And typically it's in form of uh, input parameters and return values. So print intro takes no input parameters, nor does it return any values. Um, get inputs takes no input parameters, but it returns three values: a prob A, prob B, and N. Sim end games, that's where the bulk of the work gets done. So it's not surprising that there's a lot of action in its interface. The inputs: prob A, prob B, N, and then the outputs: wins A, wins B. How many games are won by each of the players A and B? And then print summary has two inputs that are coming from main: wins A, wins B. Okay, and these are very helpful. Um, I do them reasonably often. And I mean, I've been a programmer for a very long time. If I have a program that I want to make sure that it is properly designed, and I'm kind of thinking in a sort of open and free way as to how to break the problem down, I'll draw a structure chart like this. Okay, and the good part here is typically, you're working with a pencil and paper, and as I often say, a big eraser. And you can really go through a lot of sort of alternative versions pretty quickly, and not waste a lot of time coding things that you subsequently think are are bad and give up on. Okay, off we go. Sorry about that. Okay. So when we're taking our work that has to be done and we're dividing it up, uh, one of the things that we do is we try to divide and conquer. I think we've all heard that phrase. Okay, and so the idea here is that we don't want to be worried about everything all the time. We want to divide this thing up in a way that we only have to worry about a few things at a time, and so the job at any one point is pretty manageable. So what we want to do is we want to have a separation of concerns. So at each level of the design, the interface tells us which details of the lower level are important. The general process of determining the important characteristics of something and ignoring the other details is called an abstraction. And this is a term that gets used a lot in computer science and in information science too. There are times when we want to think about something in a particular way. We want to kind of simplify it. Okay, and when we do it, what we usually do is that we think of the important characteristics in detail, and then the rest of the characteristics they're kind of grayed out. They're kind of hazy, and this ability to take something from the real world that's got lots of gnarly, thorny details all over it, and only pay attention to a subset of the details. That's abstract thinking, right? So this process is called abstraction. The top-down process is a systematic method for discovering useful abstractions. Now, this is a very powerful sentence because we've been through the top-down process since the beginning of the chapter. And what we've decided to do is we've decided to bundle up the work that we're going to do in terms of a function or a module, whatever you want to call it. And we've decided that we're going to concentrate on what are the inputs that we're going to give to that function, and what are the outputs that we're going to get back. And so that's certainly an abstraction. And then the real question for us is the current version that we talk about, is it useful, right? Does it help us to understand the program? Is this version of the program easy to understand? If it's easy to understand, then it's a useful abstraction. If it's complex and gnarly, it's like we probably haven't gotten to the right abstraction yet. For instance, this sim and games, where we take the probability of player A winning their service, probability for player B winning their service, and the number of games that we want to simulate, and then we get back the number of wins for A and the wins for B. This is a really insightful way to package up the work that has to be done. One could imagine dividing that into a couple of different pieces and having the main interact with all the pieces. But what's really useful here is that what do we want to know? Well, we want to know the number of games won by A and the number of games won by B. Okay, and then what do we have to tell it? So when we talk about useful abstractions, when we come up with a design that's really appealing, a good design, one of the aspects of it is that it just seems like a really good and useful way to do it. So we're trying to discover which of the abstractions that we might decide to put into the design, which are the useful ones, and then we pick those and we put them into the design. So now we have to design at the second level. Okay, so when you've taken the main, which has the whole job, and you've decomposed it into its component parts, then what we do is we go down the hierarchy. We go down a level. We go down to level 2, and typically we go from left to right. We go from top to bottom, left to right. Okay. And then we just do the same thing. We decompose that into subparts until we get to a part where we go, well, that's the amount of functionality that just go into a function all by itself. I could write that function. It would fit on about a page. That's fine. We don't need to decompose that anymore. Okay? So here, second level design. The next step is to repeat the process for each of the modules defined in the previous step. The print intro function should print an introduction to the program. The code for this is straightforward. Yeah, we know how to print a line or 2 or 3, right? So are we confident that we can write that code? Yeah, we are. Okay. Do we have to, are we going to have to decompose? Are we going to have to divide that into subfunctions that are going to be on level 3? No. We're fine having that chain of command end on level 2. So we can write the code. Okay. So it looks like print intro is a function that's got 1, 2, 3, 4, 5 prints in it. All right. Pretty good. And the only thing tricky in there, Zelle likes to use the double quotes on the outside. So the only thing that's at all tricky is that in this second print, he has double quotes that he wants to be part of the string, so he encloses them in apostrophes. He closes the outer string in apostrophes. Okay, so since we don't have any new functions here, while we don't have changes to the structure chart. So we've come to the end of one of these, well, we call them trees in the computer science world, but they're really root systems, right? Because they go downward, not upward. Yeah, so we've come to the end of the branches or the roots on that second level. Okay, get inputs. Okay, can we write that? Yeah, I think we can. So we're just going to write it. Okay. Let's see. It returns prob A, prob B, and the number of games to simulate. Now, I just want to point out that this kind of comment is interesting as a kind of a teaching aid. Okay, but as for a comment that you would put into a program, typically we don't want comments that kind of give a play-by-play narration of what's being done. We typically want comments that describe the intention of the code to follow. Now, when you have a function like get inputs, quite often the function name, if functions are well named, they describe just in the name of the function the intentionality of the code to follow. So you might find with some well-named functions that you don't need any additional comments at all. And this one here is probably nice for the teaching, but I wouldn't typically include it in my code. So we're getting a float A, which is the probability that player A wins a serve. Float B, so probability for B, and we have float N. How many games do we want to simulate? Okay, I'm gonna bite here. I would have made this an int. Okay, just just saying. Uh, how many is counting? That for me is integers. Okay. Um, I think it one time some older version of this slide and program, we were using eval, and somebody came through to get rid of eval, and instead of turning eval into an int, they turned it into a float. Whoops, mistake. And now we're going to return A, B, N. Okay, so can we return three values? Yes, we can. What really happens? Well, what really happens is implicitly we create a tuple that has three parts A, B, and N. Oh, okay, and we return one tuple object. Okay, then when we get it back, we can split it. Okay, so you never have to know that under the covers, these functions that return more than one thing are really returning a tuple, but that's what's going on. Okay. Okay, so now we're going to design sim end games. That was the hard one, so it's going to take a little bit of work. So this function simulates n games and keeps a track of how many wins there are for each player. Simulate n games sounds like a counted loop. Yeah, it sounds like that to me. That's why I wanted an integer for n. And tracking wins sounds like a good job for accumulator variables. Yeah, accumulator variables in the sense that they're counters. Um, so I've said throughout the course that the counter pattern is just the trivial case of the accumulator pattern. Uh, we're accumulating the values by one each time through. Okay, so this looks like pseudocode to me. So this is a nice place to go as the next step. Okay, initialize wins A and wins B to 0. Loop n times. Simulate a game. If player A wins, add 1 to wins A. Else, add 1 to wins B. Okay? And this is pretty clear. Either A is going to win or B is going to win. So we can play that directly off of the else. Okay, that makes sense. Okay, so we already have the function signature, which is to say we already know what's being passed in. Okay, so we have the def sim n games. We're being passed n, prob A, and prob B. And I'm just going to say it one more time. I think these are crummy variable names. Okay? Enough said? So simulates endgames of racquetball between players A and B, returns number of wins for A, number of wins for B. I think that's intentional enough that that's okay with me. That's not really play by play. This is kind of a metaphoric description of what's going on. So I think it adds some value. So we say wins A 0, wins B 0. Okay. for I in range n. Okay. So we want to do it n times. Okay. Now, this will do it n times. I just want to point out when we use range, is going to going to begin at the value of I is going to begin at 0, and it's going to end at n minus 1. Now that's n times through, and all we're trying to do is count the times through the loop. The variable I, the control variable for the loop, we're not really going to be paying attention to the value that it has, but sometimes we're in the body of a loop. We do pay attention to the value. So sometimes this might not get us what we want, but in this case, it's going to get us exactly what we want. So the next thing we need to do is to simulate a game of racquetball. We're not sure how to do that, so let's put that off until later. Now this is kind of a throwaway comment, but it's a really insightful point of view. Okay, if we have a concept of something that has to be done, okay, we don't exactly know how to do it, but we think that it's a proper thing to be done, like simulate one game. Yeah. Well, if I'm going to simulate a bunch of games, okay, somewhere underneath of that, I have to be able to simulate one game. Okay, so that's a great choice for a function or a module to call. Okay, now we put it off until later, the exact code that's going to go into that function. But what we're determining now is what the interface is. What do we pass in? What do we get back? Okay, so let's assume that there's a function called sim1game that can do it. The inputs to sim1 game are easy, the probability for each player. But what is the output? Well, we need to know who won the game. How can we get this information? The easiest way is to pass back the final score. Okay, the player with the higher score wins and gets their accumulator incremented by 1. I would call it a counter. Okay, but I'm always trying to make the finer points, aren't I? Okay, so here is the code for sim n games. Okay, wins A equals wins B equals 0. I just want to tell you that I don't like this coding style. Okay, this is valid Python. Okay, in most working coding environments, assigning values to two variables at the same time is considered bad practice because this is the kind of thing that you might miss. Okay. One of the reasons that he did it is he wants all the code to fit on the slide. Okay, so I'm going to give him a pass on that. But this isn't. I don't want you doing this if you're on my team. Okay. So then we say for I in range n. So we have n. That's the number of games. Score A, score B gets assigned sim1 game, and then we pass in probability A, probability B. And then when we come back, we've got score A and score B. Okay. Two values that got unpacked from a tuple that sim1 game sent back to us. If score A is greater than score B, we bump up A. Else, we bump up B. And then we return wins A, wins B. Now, what I really like about the design is it's just it's so simple. It just does what it needs to do and not anything further. So I really like the design. Okay. Uh, Again, we initialize the variables. I would have done that on 2 lines, but he did it on one. We have a for loop. It does it the right number of times. And then each time we call sim1 game and get the results. And then we bump up either the counter for A or the counter for B. So when we're done, we know that we've got proper counter values for A and B, and we return them. It's pretty sweet. Okay. Now, here on slide number 48 is a structure chart interpretation of the design of Sim1 game as it relates to SimN games. Okay, so each time Sim1 game is called, okay, we pass it prob A and prob B, and we get back score A and score B. Okay, and SimN games, which we've created the code for, it's able to process that. So the really nice thing is, even though we haven't written the code for Sim1 game, we are able to write the code for SimN games that uses the Sim1 game code, because we know what the inputs to Sim1 game are, and we know what the outputs from Sim1 game are. All right? Third level design. Okay. So I'm just going to back up. Okay. Uh, Print intro. We don't need a third level. Get inputs. We don't need a third level. Okay. Sim and games. Uh, we needed a third level, and we designed one. Okay, so now we need to do the design inside the function Sim1 game. Print summary, it's going to turn out we don't need a third level. Okay, so we only go as far down as we need to, and this kind of asymmetry in the diagram, where one or two of these hierarchy chains are deeper and more intense than others, that's typical. These problems that we go to solve, they've got kind of thorny bits, right? And in this case, our thorny bit is SimN games. And this might have a lot of subparts. In our case, it doesn't have a lot of subparts, but it's got a whole lot more than the others do. That's fine. Okay. So the next function to write is Sim1 game, where the logic of racquetball rules lies. Okay, so this, what we've really done is so far, we haven't had to make a lot of assumptions about racquetball rules. Okay, what we've been able to do is to encapsulate the racquetball rules details into one of our functions, one of our modules, Sim1 game. Okay, this is good design. We consider a design of a function, or a module in this case, to be good if it has it has high cohesion and low coupling. Well, these are two computer science words that have been popular for 40 or 50 years now. And what's cohesion? Cohesion says all the code that's in that function is about the same thing, right? What's coupling? Well, it's actually the opposite. It's the extent to which functions know about the internal details of each other. That's a bad thing. So functions should be all about one thing, okay? And they should know very little if anything at all, about the internal workings of other functions in the program. Um, One of the side effects of doing this is that you can hide a whole set of assumptions in one place. So all the assumptions about the rules of racquetball are now hidden in Sim 1 game. This is a beautiful design. Okay, so players doing rallies until the game is over, which implies the use of an indefinite loop. Good idea. Since we don't know ahead of time how many rallies there will be before the game is over, hence indefinite. We also need to keep track of the score and who's serving. The scores will be two accumulators. I'm going to call them counters because we're bumping them up by one. So, how do we keep track of who's serving? One approach is to use a string value that alternates between A or B. Okay. Third level design. This looks a lot like um, pseudocode. Okay. Initialize scores to 0. Okay. Set serving to A. Oh, okay, that means we have some string that's being taken, it's being tracked in a variable called serving, and we're going to give it the value A. Loop while game is not over. Simulate one serve of whichever player is serving. Update the status of the game. Okay, so we do that until the game is not over. So um, at the top of the loop, this is a typical test before loop, the typical Python while. We check every time for game over. So we simulate one serve, and then we update the status of the game, and then we say, is the game over? If not, we go through the body of the loop another time. When the game is over, then we simply have to return the scores. Okay, so from what we know of the rules of this game, one of the players is going to have got to 15. Okay, not two, because there's no chance to tie in these rules. So it could be 15 14, 15 13. It could be 15 to 0. Okay, but one of the players is going to have 15, and one of the players is going to have less than 15. Okay. Um, so I think what we're doing here in this bullet down here is we're taking the pseudocode design and starting to put it into real Python code. So we say, oh yeah, well there's a loop while, and what's the condition going to be for the while loop? Let's take the two scores and pass them to another function that returns true if the game is over and false if not. This again, I think, is a beautiful decision. Why is that? Well, it could be complex. Okay. Um, a lot of times, what we want to do is we want to take complexity and encapsulate. We want to put a shell around it. One great way to put a shell around complexity is to find a function to hold it. Okay, so the question is the game over? We're going to put that in a function. Oh, okay, so we're going to pass it to two scores, and we're going to get back a true or a false. True if it's over, false if not. Okay. How did he know to do that? Well, he's a bright guy. He's used to programming, and he likes this idea of hiding complexity in functions. And so he guessed that this would be a great use of one more level function. So that's a level 4 function. Okay, there it is. So you look at the structure chart, and down there we've got game over. And again, what's the interface? Well, the inputs are score A and score B. The output is a true or false, is a game over or not. At this point, Sim1 game looks like this. So we have all this code, and we say, while not game over, score A and B. So we call a game over, we pass score A and score B. What do we get back? Well, the return value is going to be true or false. Okay, so we're going to keep going until we call it and we get back a true. Pretty cool. Nice design. The alternative is that we might have had a more complex expression up here. Okay, what's nice is instead of having a complex expression about how score A relates to score B in this while, instead of that, we've hidden that complexity in game over. Really beautiful design. Okay, inside the loop, we need to do a single serve. We'll compare a random number to the provided probability to determine if the server wins the point. And we said that way back, that we would take random, which is going to give us a value between 0 and just less than 1. Okay, and if it's less than the probability, then we win. The probability used is determined by whom is serving, contained in the variable serving. All right, let's look at this. If A is serving, then we use A probability. And based on the result of the serve, either update A's score or change the service to B. What does that look like? Okay, so we say if serving equal A, if A is serving, then if random is less in probability A, bump up the score by 1. Else, change the serve. Because remember, the rules are you can only score when you're serving. Likewise, if it's B's serve, we'll do the same thing with a mirror image of the code. So this is our original code up top, and this is the mirror image. Okay, so we say else if random less than prob B. And we have these nice little comments out here. I like these because they clarify. A wins the serve, A loses the serve. B wins the serve, B loses the serve. So if B wins the serve, we bump up the B score by 1. Else, they lose the serve, then the serve goes back to A. Okay? So this design where we have kind of mirrored code, this is a nice design. Right? I think that looks quite good. It's easy to read. It's easy to understand. Okay, now putting the function together. So this is a Sim1 game. So again, we've got this loop. Okay, this is our loop right here. Okay, we see the guts of it is this nested if else. Okay, so we have an if else, and each of the sides of us has their own if else. Okay, we probably wouldn't want to get any more complex than that. And then up top, we have simplified the decision for game over by punting that over into a function called game over. Okay, then when we see that we're at the end of the game, we return score A and score B, which again are going to be put into a tuple. There's just one tricky function left, game over. Here's what we know. Okay, so game over A, B. A and B are scores for players in a racquetball game. Returns true if game is over, false otherwise. Okay, and again, this is probably good as kind of pseudocode. Okay, but when we actually have the code, I'm not sure that I would have two expressions of it. I'm not sure I would have the comment expression and then the code expression. I probably would get rid of these. Well, I'd get rid of the second one for sure. The thing that says A and B are scores for players in a racquetball game. Well, I don't know. I think I'm being too tough. This could be okay. This is kind of intentional. All right. According to the rules of the game, when either player reaches 15 points, we can check for this with the Boolean A equal 15 or B equal 15. Okay, so let's see how that goes. So what do we say? Return A equal 15 or B equal 15. Okay, so now this is an elegant, very Pythonic, very tech jock way to return the value. And now I'm seeing why we had so many comments up here. Okay, so what we did is we have a logical expression here, okay, and that's going to get evaluated, right? And then it's going to evaluate to true or false, a Boolean value of true or false, and we're going to return that. And we're going to return true if A is equal to 15 or if B is equal to 15. So one of the interesting things about these logical expressions is you can just put the expression in the return, okay, instead of having the code, using that code to load up a return value and then returning the return value. Instead of doing that, you can just put the comparison right in the return statement. Now, for a beginner, sometimes that seems extreme, okay? And I'm not going to hold you to having to do that all the time as a beginner. But I would say that this is a pretty Pythonic way to do it. Python programmers are usually this insightful about the language, and they know if there's a comparison that's going to generate a true or false, just return and put the expression in there that does the comparison or comparisons. And then print summary is pretty simple. Okay, we're getting in wins A and wins B. Okay, and so we say that N equals wins A plus wins B. Did we already know N? Well, we may have known N up higher in the program, but you have to remember what the scope of the variables are in Python. Okay, and the only variables that we know about are these two parameter variables, wins A and wins B. If we create a variable n, it's only incidental if it has the same name as a variable that's used up higher in the program. Okay, so that this is a new n. This is why it's maybe not a great use of a variable names. I would maybe call this total games. Okay, I might say total games equals wins A plus wins B, and then I would have uh, games simulated and total games, and then I'd have the wins for A and the wins for B, and then I would, instead of using N, I would have used total games. A lot of times when I name variables in these called functions, I intentionally make the variable names different than the variable names were used up higher in the program in order to emphasize the fact that they're not the same variable. Okay? Do you have to do that? No, but I think it can be quite useful. So, summary of this design process. So we started. That's all the code, right? So, for instance, if we go to the code, it's all right here. Okay, let me close this execution thing here and make it a little bit bigger. Okay, here's the main. Here's print intro. Here's get input. Here's sim end games. Here's sim one game. Here's game over. Here's print summary. Okay. Now, um, instead of just an invocation to main, he decides that he's going to check if this has been imported or not. If this has been imported, he's not going to run main. Okay. And that he uses this. Um, we'll talk about this in a couple of minutes. He uses this for unit testing, a kind of odd approach to unit testing. Okay, so this is kind of interesting. Typically, I would have not had this part. Okay, but he thinks it's a good idea, so we're going to leave it there. And again, we run this, right? So let's say this. Let's run this again. Okay. And let's say these people are equally well matched. So the player A wins 60% of his serves. Player B wins 60% of his serves. Okay. And how many games to simulate? Let's simulate 10,000 games. Let's see what answer we got. Player A won. Okay. Uh, Even though they are equally matched, player A won. Probably because he went first. That would be my guess. Player A always goes first, probably has an advantage. Okay? How about that? We ran 10,000 games pretty darn fast. Okay, so all the code's there, and it runs. Okay? Um, So, summary of the design process. We started at the highest level of our structure chart. We worked our way down. At each level, we began with a general algorithm, in this case, pseudocode, and then we refine it into precise code. This process is sometimes referred to as stepwise refinement. Okay? We are refining our definition of the problem step by step by step. So it's more refined, and then it's more refined, and then it's more refined, and then it's done. Okay? So we would take this top down process that we just had. How could we describe it in terms of a recipe? Well, here it is. One, express the algorithm as a series of smaller problems. Two, develop an interface for each of the small problems. In terms of interface, at the level of calling code versus the called code. What are the inputs to the call code? what gets returned to the calling code. That's the interface. 3, detail the algorithm by expressing it in terms of its interfaces with the smaller problems. 4, repeat the process for each smaller problem. Now, bottom-up implementation. Even though we've been careful with the design, there's no guarantee we haven't introduced some silly errors. Implementation is best done in small pieces. Okay. Now, and then he's also going to talk about unit testing. A good way to systematically test implementation of a modestly sized program is to start at the lowest levels of the structure, testing each component as it's completed. For example, we can import our program and execute various routines or functions to ensure that they work properly. And I'll show you that in a minute. So how could we do this? So we could say import rball, and then we could call rball.gameover00, and it would say false. And then we could say rball.gameover510, false. rball.gameover153, true. rball.gameover315, true. Okay, so one of the ways you can test the code in a program, in a Python program, and it's particularly interesting because of its interpreted kind of nature, and the fact that you can do testing on the in this conversational command line mode, is that you can import the program that you wrote and then test little bits of it. Is this how everybody does unit testing? No. The unit testing frameworks are much more robust than this. Is this sort of an interesting experiment in how to unit test a program? Yes, I think it is. Notice that we've tested game over for all the important cases. We gave it 0, to simulate the first time the function would be called. The second test is in the middle of the game. The two last cases test to see what is reported when either of the players has won. Now that we see the game over is working, we can go on to sim one game. Okay, so what do? Well, we say sim one game, give them equal probabilities to win when it's their serve. What do we get back? We get back two values, 11 and 15. Now, what are they in? Did I tell you that we really got back a tuple? Yes, I did. Look at the parens. This is a tuple with two values, 11 and 15. Okay, so when we have a function that returns more than one value, mechanically it's just returning one thing. Okay, your return with multiple values causes Python to create a tuple with each of the values in it. And then what do you get back in the called code? Well, you get a tuple. Okay. Sim one game, 5, 5, 13, 15. So we keep going. We can test this and see if it works the way we think we want it to test. Again, is this the way that professionals test their Python code? Probably not. They probably use a more formal unit testing framework. But this is, I think, a really cool and interesting idea, and something you can do with Python that you can't do with languages like, say, Java. When the probabilities are equal, the scores aren't that far apart. When the probabilities are farther apart, the game is a rout. Testing each component in this manner is called unit testing. Okay, so unit testing uh, is a relative term. Okay, the unit is what you're working on right now. So if you are working on it function by function, then a unit test is uh, each of the functions, right? Collectively, if what you're working on is a program, then a unit test is uh, tests of the program. They might test all the functions in the program, but the unit that you're testing, your frame of reference, is the program as a whole. The approach that we've taken here, where we try to test every function that we can, and we give them the expected inputs, and we predict the outputs. So we have expected outputs that we compare to the actual outputs. That's something that I've been trying to teach throughout the course, and that's what all the um, professional unit testing frameworks, that's the approach that they use. Testing each function independently makes it easier to spot errors and should make testing the entire program go more smoothly. Simulation results. So it's the nature of racquetball that small differences in ability lead to large uh, differences in the final score. Oh, that's our question. We're positing that question. Suppose Denny wins about 60% of his serves and his opponent is 5% better. How often should Denny win? Well, let's do a sample run where Denny's opponent serves first. Okay, so we say Denny, what's the probability? Player A wins 0.65, player B 0.6. And then we run this, and player A wins 66.6% of the time. With this small difference in ability, Denny will win only 1 in 3 games. So that's why, I mean, they've been uh, they've been concerned that maybe small differences in ability would have large differences in the number of games won. And here through simulation, we've pretty much been able to prove that to be true. Okay, now we just did top-down design. Okay, this approach, top-down design and implementation, just what you saw us do. This has been tried and true for well, certainly 45 years, a long time. Okay, and it works. All right. Is it the only way that people go about this? Well, they go about this in a lot of complementary ways. So let's go and uh, explore just a couple of the complementary ways that this might be done. Okay, prototyping and spiral development. Now, he talks about these things. These are ideas that have been around probably a lesser time than 40 to 45 years, but they've been around for a while. They've been around for 20 to 25 years, certainly. Um, One approach that's very popular these days is called agile software development, and it's kind of related to uh, this approach. So I'm going to mention agile now, and we'll talk to this prototyping and spiral, and then I want to tie it up with agile in the end. Okay. So another approach to program development is to start with a simple version of a program and then gradually add features until it meets the full specification. meets all the requirements. The initial stripped down version is called a prototype. Prototyping often leads to a spiral development process. Rather than taking the entire problem and proceeding through the specification, design, implementation, and testing, we first design and implement and test a prototype. We take many, many cycles through the development process as the prototype is incrementally expanded into the final program. Uh, how could the racquetball simulation, how could that have been done using spiral development? Write a prototype where you assume there's a 50-50 chance of winning any given point playing 30 rallies. Okay, so we don't have all the functionality that we need on probability. It's going to be fixed. And we don't know how long the rally, we don't, uh, we can't, we're just going to have rallies that, oh, I'm sorry, 30 rallies? Yeah, 30 rallies. So we're not sure exactly how long the games are. Uh, so add on to the prototype in stages, including awarding of points, change of servants, different probabilities, etc. Okay, so um, this is some of the early. So I guess this is a very early version of the program on the left, and then the results on the right. The program could be enhanced in phases. Phase one would be the initial prototype. Play 30 rallies where the server always has a 50% chance of winning. Print out the scores after each serve. Phase two, add two parameters to represent the different probabilities for the two players. Phase three, play the game until one of the players reaches 15 points. At this point, we have a working simulation of the single game. Phase four, expand to play multiple games. The output is the count of games won by each player. Phase five, build a complete program, add interactive inputs, and a nicely formatted report of the results. Spiral development is useful when dealing with new or unfamiliar features or technology. If top down design isn't working for you, try some spiral development. Okay. Here's a couple more comments here. Spiral development is not an alternative to top down design as much as a complement to it. When designing the prototype, you'll be using top down techniques. Good design is as much a creative process as a science, and as such, there are no hard and fast rules. Okay, and that I think is a really good comment because how do you get good at this? Well, you kind of get good at this by doing, and maybe by watching other people doing, right? So, and when we were taking that top down approach, we did have to have the faith that if we continued to break down the problem, that we would eventually come to the point where we would have a problem at the bottom of the chain that was a solvable problem. When you're new to this, you sometimes can lose your nerve on the way. But the fact is that you do have to have that faith. The best advice: practice, practice, practice. This is really something that you learn by doing. And the more things you try to do, the more things you work your way through, the better that you get. Now, I promised to talk about this agile software development. Okay, agile software development is not too different from this kind of approach that we took this spiral development. Actually, it was inspired by spiral development. But the fact is that there are times let's see. If we're trying to simulate a racquetball game, we kind of understand how racquetball works, okay? And we don't quite know how simulation works yet, but we're going to discover as we go. So the rules and the features are pretty easy to understand, I guess. But let's say we're trying to build a game, and it's a completely new game. Okay, okay. The probability that we're going to design it on paper in a structure chart. Let's go back to our last structure chart. Where is our last structure chart? Come on. There it is. The probability that we're going to, design the entire game. We're not even absolutely sure what the rules of the games are. What the rules of the game are. We're inventing a new game. We're inventing a new product. There are sometimes when drawing a big set of charts is not the way to get this done. And sometimes what you really need to do is come up with version 1 of the product, get some feedback, come up with version 2, get some feedback, come up with version 3, get some feedback. This is what he was doing in that spiral approach. And it's kind of what the agile approach is too. It's probably closer to spiral than agile. But and so we don't mean by showing you these structure charts, we don't mean to say that you ought to be able to take any program that you have and plan it out exactly before you begin to code and before you begin to experience it. Okay, that's it for the chapter. You're going to have some fun with the exercises, so there'll be some additional learning there. So I'm going to say bye until then. Bye bye.